Okay, in this section 5.6 we're going to talk about inverse trig functions and their derivatives. Now, as we've seen with log and exponential functions that have inverses, trigonometric functions have inverses too. But actually, since many trig functions are not one-to-one, in order to define the inverses for trig functions we have to limit the domain so that the function is one-to-one. So here are your 6 basic inverse trig functions and alternate forms. So y equal arcsine of x is the inverse trig function for sine x. Y equal arc cosine is the inverse trig function for cosine x. Y equal arctan is the inverse cosine for tangent. Y equal arc cotangent, inverse function for cotangent. Y equal arcsecant, that's the inverse function for secant. And y equal arc cosecant is the inverse function for cosecant. Now, one thing I want to warn you about, don't get this confused with the reciprocal function. Like, for instance, arcsine is not 1 over sine, which would be, let's see, how do I remember that? 1 over cosine is not cosecant, it's secant. So 1 over sine would actually be cosecant. So that's not what this is. This inverse right here does not mean, you'll hardly ever see anyone try to talk about the reciprocal of sine x using this -1 just to avoid confusion. So if you see this notation here, sine with the -1 here of x, that's actually the arcsine of x. And some people prefer this notation just to avoid anyone thinking about reciprocals, because they're definitely not reciprocals. Hopefully I've made that point to you by now that they're not reciprocals. Arcsine is not the reciprocal of sine. It's the function. So it's actually the function that if you applied arcsine to the sine function, you would get x, or if you applied sine to the arcsine function, you would get x. So basically it's just the function that undoes whatever the sine function does. Okay, so maybe a better way to look at that is just look at what I wrote here. Y equal arcsine x is equivalent to saying that the sine of y equals x. So if you think of it like that, it might make more sense. Y equal arc cosine of x is equivalent to saying that the cosine of y equals x. Y equal arc tan x is equivalent to saying that tangent of y equals x. Y equal arc cotan is equivalent to saying cotangent of y equals x. And y equal arc secant is equivalent to saying secant of y equals x. And y equal arc cosecant of x is equivalent to saying that cosecant of y equals x. Now, the domains that are used for these functions are listed over here. So you can just make note of these, you can take a picture of these, or whatever you want to do here. But these are the domains and their corresponding ranges that are used. Now remember, the domain has to be limited so that the function is one-to-one. Okay, so now let's look at the arcsine function. Okay, so basically what we're doing is when we have the arcsine function, we basically have the domain is -1-to-1 and the range is pi over 2 to pi over 2. And actually this function is derived as the inverse of the sine function. So if you look over here, you'll see the sine function and its domain is pi over 2 to pi over 2 and its range is -1-to-1. Let me mark this up for you. Okay, so let's take a look at this sine function here. The sine function right here is actually, we're going to limit the domain of this sine function from, that should say minus pi over 2. So actually from minus pi over 2 to pi over 2 for the domain. So you can see here I didn't have a pi symbol for this, but minus pi over 2 is the leftmost portion. So it goes, so this point, the x value here at this point is minus pi over 2, and the x value here at this point is plus pi over 2. Now I drew these two horizontal lines to show you that the range goes from y equal -1 here up to y equal +1 here. So that's these two horizontal lines. So now remember, for the inverse of a function, the domain and range swap places. So the x values for the arc sine, which is the inverse of sine, would actually go from -1 to 1. So the domain would be from -1 to 1, where the range would actually be from -π/2. So this point down here would be -π/2 for the y value, and up here the y value would be π/2. So basically that's what the inverse of the sine function would look like. Okay, for the arc cosine, I decided to just go ahead and freehand it here for you. So the arc cosine is the inverse of this function, y equal cosine x. But to get the arc cosine function, you have to limit the domain for the cosine function from 0 to pi. So x goes from 0 over to x equal pi. And when you do that, you just get this piece of the function. And then over here, when x is 0, the cosine of 0 is 1. And then when x is pi, the cosine of pi is -1. Now if you flip-flop the domain and range, what you get over here is the arc cosine function, where x is -1, x goes from -1 to +1, and the range goes from y equals 0 up to y equal pi. So that's what the graph of the arc cosine function is. And one thing I didn't mention a minute ago, like this point over here is actually the point pi -1. Well, if the point pi -1 is on the graph of this function, then the point -1 pi is on the graph of its inverse, and that would be right there. And then this point here is the point 0, 1. And so if the point 0, 1 is on this graph, then the point 1, 0, which would be this point here, would actually be on the inverse. So that's the cosine function and its inverse. Okay, for the domain of tangent, for the tangent function, we limit the domain to go from only -π/2 to pi/2. And if you remember, pi/2 and -π/2 are vertical asymptotes for the tangent function. So if we go from -π/2 to pi/2, then that allows, since these are vertical asymptotes, that allows the range to go from -infinity all the way up to +infinity. Okay, well, on the arc tangent, since it's the inverse, we got to flip-flop those. And so then the domain would go from -infinity out to infinity, and then the range goes from -π/2 up to pi/2. And I'll correct these in the notes, but those should be minuses, pi/2 for those two spots there. Okay, if you want to freeze the video, and you can take a picture of the other three inverse trig functions here. They're graphed here. If you want to research some more, you can online if you want to. Here are some properties of the inverse trig functions. As long as, if you think about the sine of the sine function, as long as x is between -1 to 1 and y is from -π/2 to pi/2, then if you take the sine of the arc sine of x, you get x, or if you take the arc sine of y, you get y. So basically, if you apply the sine function to its inverse, it's just going to return the argument, or if you apply the inverse of the sine function to the sine function, it's going to return the argument. And again, it's got to be within this specific domain and range. And also, using the domain and range for the cosine function, the same thing would be true for cosine and arc cosine. Cosine of arc cosine of x is x, and arc cosine of y would be y. And then for the tangent, you just have to make sure that y goes from -π/2 to pi/2. Then the tangent of arc tangent of x is x, and the arc tangent of y is y. And then there's also three properties here for the other three functions, but some of them can be a little more complicated. This one's not. Cotangent and arc cotangent are not too complicated. Y has to be between 0 and pi inclusive, and then you get that the cotangent of arc cotangent x is x, and the arc cotangent of cotangent y is y. For these other two, you've got to have absolute value of x is greater than or equal to 1. So in other words, x has to be greater than or equal to 1 or less than or equal to negative 1. And then y has to be from 0 to pi over 2, including 0, or pi over 2 to pi. And then in that case, secant of arc secant x is x, and arc secant of secant y is y. And you get a similar definition here for cosecant. Cosecant of arc secant of x is x, and arc cosecant of cosecant of y is y. So I'm going to solve a couple of equations. I'm not going to worry about the domain and ranges. I'm just going to assume they'll work out here. So arc tangent of 2x minus 3 equals pi over 4. What you can do there is you can take the tangent of both sides, and then you get tangent of arc tan is equal to tangent of pi over 4. Well, tangent of arc tan of 2x minus 3 is just 2x minus 3, and tangent of pi over 4 is just 1. So then you get 2x minus 3 equals 1, and then you can just simply solve that for x, and you can get x equal 2. Here you have a cosine of 3x is 0, so if you just apply the arc cosine to both sides, then you get that the arc cosine of cosine is just 3x. And then for the arc cosine, you have to decide, well, the cosine of what value, what angle is 0, and the cosine has to be pi over 2, because it has to be within the particular range that we're using for cosine. So 3x must equal pi over 2, so x must be pi over 6. Okay, I'll show you here how to find the derivative of arc sine of x, and then you can just snap a picture or pause the video and read the one for arc tan of x, but you're going to find them in a similar way. First of all, if y equals arc sine of x, then you're going to take the sine of both sides, and then you get sine of y equals x, because sine of arc sine of x is just x. And then you can implicitly differentiate, and if you take the derivative of both sides implicitly, well, the derivative of sine of u, remember, is cosine u times u prime, so the derivative of sine of y is cosine y prime, and then the derivative of x with respect to x is 1. And then to solve for y prime, you just divide by both sides by cosine y. Now let me show you over here the angle y. Right here we know that sine of y is equal to x over 1. And since sine is opposite over hypotenuse, we know this must be x and this must be 1. And then using the Pythagorean theorem, we can show that this side must be the square root of 1 minus x squared. So now if that's true, then cosine of y, remember, would have to be adjacent over hypotenuse, so that would be the square root over 1. So you get 1 over that square root over 1, which is just 1 over that square root. So y prime would be 1 over the square root of 1 minus x squared. So again, if y is the arc sine of x, then y prime would be 1 over the square root of 1 minus x squared. Now, if the argument was a function of x rather than just x, then you would still get this as the derivative, but in the form of u, you'd have 1 over the square root of 1 minus u squared, but then you would have to multiply by u prime because you have to invoke the chain rule. And again, you can easily do the same thing over here by taking tangent of both sides, and then you'll actually be able to show that the derivative of arc tan of x is 1 over the square root of x squared plus 1, and then the derivative of arc tan of u would be that same form, 1 over square root of u squared plus 1 times u prime. And on the next video, I'll show you all of the derivatives of the arc tan or the arc functions and some examples.